All right, let's now talk about some stuff. Before that, let's have some quick reminder. Your lab number 1 is due this Friday at noon, not midnight. All right, just make sure to submit before the deadline. The submission will be closed automatically after the deadline. So please make sure submit your best attempt before the deadline. And shortly after that deadline, I'm also going to release your lab number 2. So that will be some interesting problem for you to think about. So no longer like lab number 1, where you kind of being spoon-fed about some tutorial for rodent. But for lab number 2, you will be able to apply what you learned in lab number 1 in a different problem. Interesting problem, actually. Okay? And for the scheduled lab tomorrow, it will be optional since we don't have a test. But I will be there myself, and also TAs will be there. If you want to discuss any course material that we're going to cover today or earlier, or if you want to talk about lab number 1, feel free to come. I'll be there. Also, TA will be there. And we'll just continue with the math review this week. Hopefully, early next week, maybe Tuesday, we can finish our review, and we can move on to the case study. That'll be roughly the plan. But it's really important to get all the math clarified before we move on to the case study. So that will be very crucial. Let's take a very quick recap of what we discussed last time. So last time, let's now go back here. Right, we talked about this idea of model, like a correct by construction. Make sure you really know what that means. And we got model-based developments where we got a series of models over here, right? Guys, please. All right, so we got model-based development here. We got a series of models. You want to make sure we're starting from the most abstract until the most concrete model. And we got to make sure every individual model is somehow formally proof as a refinement of the predecessor. And we talk about the two case study. We'll definitely get into much more details for the bridge controller later in the course. And this one here, I'm hoping that we'll have time. We'll see. And we started reviewing the math, especially propositional logic. And implication is something we spent quite a bit of time last time. We talk about a truth table for implication. We have to make use of it when we talk about some proof strategies today about quantifiers. So you want to make sure you understand the truth table. And we talk about the different ways to refer to the P implies Q, right? In the slides, we talk about 1, 2, 3, 4, 5. Each one of them is really trying to address how the truth table is being structured for the implication. So when you study for that, you just have to convince yourself, for example, how this one here is really covering all the 4 cases in the truth table for the implication. That's how you should really study yourself. And we talk about if and only if, right? And we talk about inverse, converse, contrapositive, right? That's just one of the results. And this is where we were to end. We talk about the quantifiers for predicate logic. Let me just show you some slides which I didn't show last time. When we move from propositional logic to predicate logic, it is really important to know what the extension is. Okay, somehow, okay, sorry. I'm losing my cursor. Okay, there we go. Okay. All right, so you can see from the slide there are some basic propositional logic definition. For example, you can see P implies Q is equivalent to not P or Q. And we can apply this today to prove some interesting property of quantifiers. Just some nice exercise. And we talk about identity, right? That's something we talked about last time. And the 0 of the implication, we also talk about it. And De Morgan, very basic, right? You can just make sure you brush up your mind about it. And also double negation, also basic. Contrapositive, we talked about it last time. Okay, predicate logic. What's really a predicate as opposed to a proposition? We are really talking about some universe of disclosure. That's a formal term. It really means we are talking about a variable or variables over certain ranges. It could be over from 1 to 10. It could be over the entire integer set, or it could be over the entire natural number set. So we're going to define what integer and natural numbers are, just to be precise, so you know when to use which in this course. So whenever we talk about universal disclosure, it's just mean a range, right? And we got two ways to quantify over the variable, either universal or existential. We'll dive into much more details today in just a moment. And of course, range over here, right? Let me just go a little bit more on what we said about these two quantifiers first. And I would like to make some connection to your 1021 when you learn about Java, right? That might be something you haven't really thought about. It's actually quite related to logic. Right, so now let me just go back there. If you remember, this is where we were last time. We'll talk about the syntax. Let me just recap very quickly. And then we're going to use the same page, but I'm going to develop a little bit further to link something to Java. Okay? Universal quantification, existential quantification. And the Boolean, sorry, not the Boolean, bullet. There should always be a bullet. So the way we write this predicate here is just consistent with how you write it in rodent. Of course, in the most general form, you might have something like this. I'll get back to this in a moment. In the most general form, you might just have, for example, for every some variable I, and then you just have a single formula. Let me just say, not to confuse with it, since we got R and P, right? You can just have Q of I. You can think about the implication you have over here is substituting this QI, right? I'm just using a more specific form that's used by rodent. There's an advantage to really specify your universal quantification this way using implication. Similarly, if you have there exists some variable I, you can say QI. This will be the most general form, a single predicate over here. But we're just using a specific QI being a conjunction. There's also some advantage of using this to explain certain base cases and strategies. All right? Let me just go back here and just remind you here. Right, we got implication here, we got conjunction over here. The meaning will be, in order for this universal quantification to be true, it should be that every possible value for I, they should really satisfy this implication. But I'll dive a little bit deeper later. Also, in order for this existential quantification to be true, you should find at least one witness, we call it, for I, such that this conjunction can be true. All right? That's also a brush up, from 1090. And remember, I asked you this question over here, right? What happens in each case if, for example, this one here is empty range, meaning that it's false? False means no element can satisfy this R range, so it's empty. And what happens when this is actually empty or false? Right? That's what that's what I ask you to really consider over the weekend. And I would like to take it from here and mention something to you. That over here. So now the question is, here, this is the range. What if empty range? Meaning that not the case, R, I. Or you can say Ri is equivalent to false, right? Similarly, we got a question here. What if, I'll just write another way, Ri is just equivalent to false? Right? Well, I'm saying the two, something's identical. And I want to draw some quick connection to your Java code from the first year. Let's say I have some method over here. The first method here goes like this. It's an accessor. It's going to return a Boolean. Let me call it all positive. And it's going to take some input integer array A. I'm pretty sure you know how to implement this. Given an array, which may or may not be empty, I want to return true if all the numbers in the array are positive. Otherwise, false. Okay? Let me put another method here so we can compare. Another method here is Boolean let's say some positive. Over here, also takes as input an integer array. And this one goes a little bit the opposite way, the symmetric way, to say if there is at least one number in the input array that's positive, return true. Otherwise, return false. Okay? Now, when I ask you about the question of the logic over here, empty range, I'm really considering empty input array. And when I'm asking about whether or not all elements in a single array, like a range, satisfy a particular property, for example, being positive, I'm really doing some universal quantifier implementation. Similarly, for this one here, if there's at least one number in the array, in the range, I'm really asking existential quantification question. Right? Good. Having said this, I want to ask you here. Let's talk about base case. I'm pretty sure the non-base case, when the array is not empty, you know how to use a loop. That's not the focus here. I just want to do here. If a dot length equals 0, that's empty. Now I want to return some value over here. I'll put a placeholder over here. Similarly, I say if a dot length equals 0. And then I want to return something here. All right, like that. Okay? Let's say this is case number 1. This is case number 2. All right? I'm not sure if maybe you are kind of struggling about, oh, what should I put in the base case? Should I put true for empty array for both cases, or should I put false for empty array for both cases, or maybe I should put different true or false for different cases? I'm now telling you somehow it's connected to what we're talking about over here, right? What about case number 1? When I got the input as an empty array, what should I return? True? False? Okay, there's nothing there. Okay, let me temporarily put false. Okay, temporarily. But I can tell you true is right. But let's say this. If you say false, right? The way to think about is this. In order to figure out what to return for the empty array, think about, in order for me to find out if all the numbers in this array is positive, can you find a single number that proves otherwise? That means, can you find a number that is going to dissatisfy the positive property? Can you? Oh, so the question again is, okay, let me put it down. All positive, right? Now, here's my question. Sorry, I should have made it clear. Can you find a number in A, in array A, in input A, that shows otherwise? Because my goal is to really find out if all the numbers in this array is actually positive. So another way to really put it would be, can you find any witness in this array that will prove otherwise? Can you or can you not? Yeah, array is empty. In this case, can you find any witness? Not really, right? Because it's empty. There's no way for you to find any witness. Since you cannot find anything to disprove it, so it should be true, not false. Okay? This was maybe a little tricky because you want to think of the other way. In order to prove something that's true, you want to think about, can you find any violation case to prove otherwise? If you cannot, that something must be true. Right? That's what I'm saying here. So it's true. And if you look back to the logical counterpart over here, if the range is actually false, we know pretty well by the zero of implication, false implies anything will just be true. Yes. So So now we do see some correspondence. All right, so here it will be just true. So this is called the zero of implication. Let me recap. I would just like to show to you the programming logic here is really following the universal quantification logic. They have some correspondence here. When I want to consider if all the elements in the array satisfy a certain property, for example, if they are all positive, in the base case where the array is simply empty, the way to decide what to return, you can either just go back here to say, oh, if the range is false, in that way, false implies anything, so I should just really get true. That's one way to think about it, just a logical correspondence. Another way to think about it is, if you want to prove that something is actually true, can you find something to prove that it's false? If you cannot find something that proves that it's false, then that something must be true. I cannot disprove it. I cannot contradict it. All right? That's the for all case. You can try to think about it. It's kind of interesting connection. So if you ever have to show people how to do this base case over here, they might just ask you, why are you returning true? That's something you want to kind of explain, right? Because no witness can be found in empty array to prove otherwise. You cannot find any negative number in the array to prove that it's not all positive. Okay? Well, the second case is slightly easier to see. So we got some positive over here. In order to prove it, you must find at least one number that's positive. Now, are you able to find any witness in the array to show that it's positive? Not really. Empty array, just empty. You can never find anything in the empty array, right? So that's why this one here should be false. Because no witness can be found in the empty array to prove. All right? And let's look back to the logic. In this case, if I know the range over here is false, one of the operand for the conjunction is already false, overall it should be false. So we also have some nice correspondence over there. Yeah, I would say this example kind of show nicely between programming and also the logic, since you have to write for loop quite often, in your programming language. So I think showing some connection might be nice. Any question about this? We good? Okay, I hope that's clear. All right, so let me just do one more connection to the programming, and then we can go further about how we can prove and disprove more generally about for all and exist. Let me just diverge just slightly. That's something I wish I could do last time. Let's do it properly now. Okay. Let me talk about conjunction, disjunction. Here. Right, truth table, I'm pretty sure you know. And I want you to tell me, well, before I tell you the answer, conjunction, disjunction, right? Logical operator versus ampersand, or in Java, or maybe in other programming language, they may have a different syntax, but I'm pretty sure they support the so-called logical operator as well in the programming language. Are they really equivalents or not? Have some thought. I'll tell you some story here, but anyone? You think they are the same? Okay. Do you think they're the same? Why not? Tell me one occasion where they're not the same. Or just intuition. Oh, did I say that? Okay, baby, yeah. Yeah, sure. I'm glad you trust my words. Yes, they are indeed different. But let's see why they are different. Anyone who would like to share some insight? Yeah, go ahead. Why are they same or different?
I was saying, like in Java,
Okay, say it again. Sorry, let me just make sure I follow you correctly. In Java, you're saying that, okay, let's say if I got this, right? Let's say if I got P and Q. Say it again, please.
So in Java, both are the same. Like, for example, both are false and some other in Java.
Not really. If this is false and this is false, you will still get false. That will be the same as logic. So let's say this is true, this is false, you will still get false, also according to logic. I would say if you just try to evaluate true, false for different combination, you will just see the truth table. Over there, there's no contradiction. Maybe that's what you're referring to, right? It's not exactly there. Good try. Thank you. Anybody else? I'll give you a small hint. Have you guys heard about something called short circuit? You have, right? Okay. Can anybody tell me what short circuit is? Here, first of all, you want to get this one here. How about just for this one? What will be the short circuit for the logical operator in the programming? Short circuit, can anybody tell me? Go ahead, please. Exactly. So short circuit tells you you don't necessarily have to evaluate left and right always. You try to go evaluate left first. If the left is already false, you don't bother with the right-hand side. That's exactly right. Okay? This actually comes from the truth table because we know that if the left-hand side is already false, if the left-hand side is already false over here, it doesn't matter what right-hand side is. It will just be false for conjunction, right? Okay, let me just write it down. Whenever we want to evaluate P and Q, so we'll evaluate in general from left to right. Left to right. If the left evaluate to false, the evaluation of the right is skipped. Of the right is skipped. And of course, when I talk about the left, I really talk about the P. And when I talk about the right, I really talk about the Q, right? That's a short circuit for conjunction. And of course, you will know what the corresponding short circuit is for OR, right? That's something I will leave to you. Do we have this when we have conjunction over here? If I got P and Q in logic, do we have such thing? Do you have to say, if I want to evaluate P, well, true, sometimes you might want to take some shortcut to say, I want to evaluate P, and if P is already false, maybe I wouldn't evaluate Q. Maybe that's a shortcut, right? But thinking in logic, typically, we have to evaluate both sides to make sure they are well-defined, in the sense that both expressions must make sense. Number one, both P and Q must be well-defined. And I'll show you one example, what well-defined really means. You might run into something like that in Rodin later. Both P and Q are well-defined. And also you have to somehow evaluate both sides separately. Right, so that's the critical difference, which I'm going to show you one example to see interesting facts. In logic, whenever we talk about conjunction, for example, you have to make sure both sides can be evaluated. So that means they have to be well-defined. And then once you evaluate P and also Q, you can put them into the truth table like this. In the programming world, we are more talking about efficiency. And sometimes we also assume a particular order of evaluation. We always go from left to right, evaluate P and then evaluate Q. In logic, we don't really do that. We think about evaluating these two separately in parallel. So here we got P and Q, and if P is already false, we don't worry about Q. Skip it, right? There's no such skipping thing for logic. And I want to show you just one example over here, concrete example. And that'll be it for this discussion. And the practical example will be array indexing. All right, let's take a look. I want you to take a look at this example here. So we have accessing array. All right, let's say we assume A is an array of size 10. So you got indices 0 all the way to 9. Right? So A dot length is equal to 10. Okay. Now, let me show you one thing and tell me if there's anything wrong. Okay. Number one. Let's say I want to go into index I, and I want to know whether array A at index I is larger than 10. Let's say that's my intention. Let me write down the following expression. I less than A dot length. AI larger than 10. I larger than or equal to 0. All right, possibility number one. Let's say that's my Java code. I want to know whether or not AI larger than 10. And I'm kind of putting some conditions surrounding it to make sure I should not be too large and I should not be too small either, right? Does this Java code work? Does it work always? Does it fail always? Or it works sometime and fail sometime? Sometimes, right? Okay, that's good. That sounds like a good answer. Can you tell me when does it not work? How about that? You mean if AI is less than 10? Oh, that's okay. You know, if AI is less than 10, in that case, this will just be false, and somehow I might just get a false result. So when I say it doesn't work, I don't really mean it's going to return false. Returning true or false is okay. It's a Boolean expression anyway. It's okay to return true and return false. What I'm talking about is, when I say it doesn't work, I mean it crash, like an exception. A negative number? So, for example, okay, let's try. I like that. Let's try together. Let's say I is simply, you said negative, right? Let's say -2. How about that? Okay, sure. No problem. And how do we evaluate this at the runtime? We're going to go from left to right. Agree? So let me call this 1. Let's call this number 2. And call this number 3. Okay? So now, number 1 over here, I less than A dot length is going, basically this will be -2. This will give us true, right? And then in that way, we're going to, because of short circuit, we have to evaluate this as well. And then when we get to 2, we're going to evaluate A at index -2 larger than 10. This is going to crash, indeed. Right? Indeed. So it doesn't work always.
What if we had a quantifier? So,
but we don't have quantifier in Java, right? So we're still talking about Java. So here, yeah, just don't get confused. We're just talking about conjunction, disjunction here. All right? On the other hand, let's say if we have, so this is the case where it might fail. What about a case where it will succeed? Let's say I is equal to, let's say something very big. Let's say 100. Apparently it's invalid index, right? Apparently. And when we evaluate 1 over here, so 100 less than A dot length. So A dot length we know is 10. So this is going to be false. because a short circuit is going to have false over here, so do we bother to evaluate the rest? Not really, so it will be skipped. So somehow we are protecting the constraint, right? So now, because this is false, so AI larger than 10 is skipped. And the expression just evaluates to false overall. So this is just to remind you about how we may use the conjunction over here, right? Just by the order of the constraint over here, sometimes we might let it fail, sometimes we might let it pass, right? So you got to put it properly. By the way, what will be the correct way of doing this so that we don't have any fail? That will be the follow-up question. Would you like to suggest something for us? Since you identify where it might fail, how do we rewrite a Java code over here such that we don't have that failure situation? How would you suggest?
I guess we could push this statement, I guess an if statement, make sure it's
No, we don't really need an if statement. It would be even simpler. Right? Anybody? Yes.
Can we put that third condition first?
Yeah, if you put a third condition, basically you want to reorder the expression here because short circuit is really from left to right always. So the order of evaluation is important. All right? Right, let me just write it down and then I'll make a final remark and we are done with this example. So the correct way of doing things. Number 2, if I say, let's say I less than a dot length and also I larger than or equal to 0 and AI larger than 10. This will be the correct way of doing things over here. We call these over here the guarding constraint. Guarding constraint, meaning that if you fail any one of these, this evaluation is going to be bypassed. It's going to be skipped. That's why, so now having this -2 is going to fail this particular guarding constraint. It's going to be false, and we can avoid evaluating this and have the crash. So we don't have that crash anymore, right? This is just a review of the short circuit. And now the question is, do we have such mechanism in logic? Not really, right? So when you evaluate P and Q, not really. Okay? So let me say a final thing, and then that'll be it. Now I want you to think about what will be the corresponding writing in math. Okay, I'll put it here. So if I have, let's say, I less than, I'm talking about this one here, I less than a dot length. So conjunction here, I'm talking about math. And I larger than or equal to 0 and AI larger than 10. Right? Let's consider this math expression here. Now, we don't really have that effect of the guarding constraint. We don't really. If you put this into Rodin or any formal specification tool, it's going to complain to say AI over here, let me just highlight it, is not well defined. Or ill-defined. The idea would be, whenever you put any conditions in parallel using conjunction, they are independent. So this is independent of this, which is independent of this. They are completely independent, separate. In order for this AI to really make sense, I here should satisfy certain constraint. That should be put in some assumption, right? But it's not the case because we got conjunction over here. So that's why if you put it in a tool like Rodin, they're going to complain. AI is not well defined. But you don't have such stuff in programming, right? So that's why I'm saying they are not exactly the same. You might be thinking, in order for this one to work, in order for this one to be considered well defined, maybe we can have some antecedents for the guarding constraint, right? I'll put it down and then discuss that briefly. An alternative over here would be, I might say I less than a dot length. And I larger than or equal to 0. That one implies, so this is a different operator I'm using, implies, and then AI larger than 10. Right? You can see now we got some antecedents. And if you remember, there is a proof strategy called assuming the antecedents. So now we can actually assume these two are the case and prove this. But now we're kind of away from the conjunction already. So to really do things properly, just doing conjunction is not the way to go in logic. That's my point. Guys, are we okay about this? Might seem a little bit confusing because it's in its nature it's confusing. Because we are using the ampersand in a programming language like a Java, and we declare them as logical operator. But in effect, they are not exactly logical. Not exactly. Because they got a short circuit evaluation. So that's why I'm trying to compare how they are different. It's important for you to notice as well. Okay? Any question about this? Yes. Sorry, say it again. I don't quite catch you. Sorry.
So when you say it's still defined expression,
Yeah.
is it for like the second case?
Okay, in both cases. So if you only talk about, about definiteness, right? If you only talk about programming, no issue there. Because for the programming, when you get to it, you just try to evaluate. If you crash, you crash. But now in logic over here, whenever you want to have an expression like an AI, now at this point, can you assume anything about I? In this case, if you only got conjunction, all the predicates over here are supposed to be independent. So you cannot assume them. They kind of happen at the same time. On the other hand, in this particular predicate, which doesn't use conjunction throughout anymore, in this case, we can assume the antecedents and use them to prove that this is well-defined. It's okay. All right. Good. All right. All right, it's good for your knowledge to know about the difference between logical operators in a programming language versus the real logical operator. Important. All right. Okay, why don't we move on a little bit, and then we should take a very short break. Just one more thing. How about that? All right, let me go back to the slides and go over a little bit, and let's do some example. And we can pause for a break before we talk about proof strategy. I think that'll be a nice break. All right, come back here. All right, back to logical, back to predicates. And we're going to use some symbol convention. You have seen them already in lab number 1, but let me just remind you. Okay, let me just open a new page over here. First of all, we got the Z over here will be the set of integers. So we got this one here, right? So this will be set of integers. Of course, we'll start from minus infinity all the way to minus 1 and 0 and then 1 all the way to plus infinity. And the next one could be confusing for some of you because I know in different math course they might define natural number set differently. But let's talk about how we define in this course, which is consistent with Rodin. Natural number. Set of natural numbers. Right? It would be basically from 0 and then 1 and then 2 and all the way to plus infinity. Okay? So you just have to know you got 0 included in the natural number. And I'm pretty sure you have seen that in the lab 1 as well. If you want to say, how about just positive integer? You can also say natural number but 1. It will be starting from 1 and then 2 all the way to plus infinity. I think for some of you, this might be the definition you're used to for natural number, but not for this course, right? Natural number, by default, including 0. If you want to exclude 0, one way to do it is by referring to this set. Okay? Or you can just put an extra constraint to say the number should be strictly larger than 0. Right? I'll leave that to you. Okay, one more about some syntactic reminder. Okay, so here you can see we got only I here is a single variable, just for simple illustration. But in general, you may have more than one variable over here. So how do you do that? I'll show you the syntax quickly. So if you want to have, for example, two variables, you say for every I, comma, j. If you have multiple variables, separate them by comma. Okay? And then over here, ij. And then you have to specify the range, for example. You can say I is a natural number. It's a member of the natural. And also j is integer. And then certain property should be satisfied. Effectively, if you want to implement this for all, how would you implement it? Basically, got two loop counters. So you may need to have a double nested loop, right, to implement that. You want to make sure you range over I, conceptually over all the natural number, range over j in the loop over all the integer numbers. That'll be a double nested loop, conceptually. Okay? So here we need to consider all combinations of I and j. But of course, once we reach out to the proof strategy, sometimes you don't really have to consider all the combination because it could be infinite. If you can find out one witness in this combination that can prove otherwise, you can disprove the universal quantification. Or if you're able to maybe argue about all the combinations in a slightly more abstract way, you don't really have to go over one by one. Right? That's something we shall see over the course. Right? But the main thing for you to learn is about comma separated variables. Right? If you want to use it in your labs, you can feel free. Why don't we go over some example for all and exist, and then we'll take a short break. Okay? And we already learned about the meaning about for all and exist already, so why don't we consider one by one. Let's see what your intuition might be. This might have some good warm-up for the proof strategy that we're going to do after the break. How about this one here? We're saying that for every I, if I is a natural number, that implies I is larger than or equal to 0. Is that true or false? True, right? This one here is quite easy to argue in an abstract way. Because this range here tells me I would be 0, 1, all the way to plus infinity. And I know that I larger than or equal to 0 is already satisfied over here. This is larger than or equal to 0. This is larger than or equal to 0. And of course, this will be larger than or equal to 0. Of course, I know we don't really compare infinity, but I'm just writing that out. This will be true. In order to show the universal quantification to be true, one way to do it is you have to go for every possible value for the variable and argue that they satisfy the property, which is over here in this case. This is one way to do it. All right? In this case, it's not bad. What about the second one? For every I, if I is an integer, that means I is larger than or equal to 0. False? Okay, how would you prove it? If you want to show I'm claiming to you, every I satisfies this. If you want to prove that it's false, you want to just give me one I, that's going to disprove it, right? What would that be? Give me one. Negative 1. Yes, you're going to give me a concrete witness. This is going to be false, and I just need a witness. Minus 1. So let's be a little bit more careful here. We know that minus 1 is a member of the integer. And does that imply minus 1 larger than or equal to 0? Now really, you can see this part over here is true. and this part over here is false. True implies false is going to be false. Right? So overall, universal quantification is false. Okay. What about this one here? We got I and j. Right? We say for every combination of I and j, I is an integer, j is also an integer. It's either that I is less than j or I is larger than j. True or false? I heard false. And give me a witness if you think that's false. Equal? Give me some concrete witness.
Like where I is equal to 1 and j is equal to 1?
Yeah, exactly. Yep. So here, this would be false. And the witness, of course, you can either say when I is equal to j, but it's good to give some concrete one. So for example, I is equal to 1 and j is equal to 1. And it would be your exercise to apply this one over here and plug it in to the implication and show that it's false, right? Like how I did it for the previous example. Okay, I'll leave that to you. All right, let's do existential, right? So I think somehow we really get some very nice feel about how we can prove or disapprove, but we're going to see a little bit more closely, more formally to see the strategy for universal and existential. But we'll do that after the break. Let's do one more, please. Let's say this one here. There is at least one I such that I is a natural number and I is larger than or equal to 0. True? Now, the way you prove about existential doesn't seem like you have to find out all the possible I, right? You just want to find such I, because I only assert there's at least one such I. So what will be the witness? 0. I agree. Yeah. Thank you. That's true. And the witness to show this will be 0. All right, one more. How about this? There's at least I, that's integer, and larger than or equal to 0. That's true, right? Yeah, I agree. So I'll just give you one, let's say 3, for example, right? Or 0. I'll just give you 3. All right? And finally, you can see this example here basically is compare this and this. I just changed from universal into existential. And of course, the pattern over here also changes. Used to be false for universal. Now, what about for existential? True? Give me a witness. 2 and 3? Yeah, I agree. So here, it will be true. So the witness will be I is equal to j is equal to 3, right? So now, very easy. If you plug it in into here, 2 is an integer. 3 is an integer. That's good. 2 less than 3, true. 2 larger than 3 is false, but that's okay because it's disjunction. So you still get true. All right, so overall, you still get true for existential. Question? It does, it does. So let me, yeah, that's a good question here. Does the universal quantification always need it implies? In general, no. I think in general, let me just go back. I think it's good to clarify again. In general, you just have some form of predicate after bullet point for universal or existential. However, for our purpose, we're going to use Rodin. So Rodin has its pattern convention for easy proofs, right? So in that way, they simply have the implication for universal and conjunction for existential. Yeah, just kind of the heuristics that we're applying for this course. Yeah. Good question. All right, why don't we take a 2 minutes break, and then after the break, we're going to talk about proof strategy for these two quantifiers. Take a short break. Yeah, before the break, we talk about some informal example for universal and existential quantification. Let's talk about proof strategy. It's also worth knowing. So if you go on the slides, it's already there, but I would like to go over point by point together with you. It's actually quite important to know. Universal, these are just informal meaning. You can go over that. We already covered it. And this slide here about the syntax for universal quantification also covered. And these are the examples we did before the break. Let's now talk about proof strategy. Okay? And it is because we put the universal quantification in the implication form. So we can talk about some specific strategy more easily. Right? Let's now go one by one. Right? I'm switch to here. All right? There will be 4 strategies that we're going to talk about. Each one of them might involve more than one. Right? But I would say this. 1, 2, 3, 4. Right? For universal, we have to know how to prove it or disprove it. For existential, we also need to how to prove it, disprove it, right? So that's why we got 4 cases here. And since we put universal quantification in the implication format, and also here, when we say to prove it, you really are trying to argue that this implication here is true. When you are trying to disprove it, you're really trying to argue that this implication is false. So now that's why the truth table that we talked about last time could be handy. Right? That's something for you to know first. Similarly, in order for us to prove something about existential quantification, since we got conjunction, so we want to show that this conjunction is actually true. And for this one here, if we want to disprove the existential quantification, we want to show that this conjunction is false. Right? Conceptually, that's what we're going to do. Right? Let's go one by one. Okay? How do we prove? Here. Case number 1. So now if you want to prove the universal quantification, your goal is to show that this predicate here is true. R of I implies P of I is equivalent to true. Now, according to the truth table, how many ways are there for you to show that the implication is true? 3? Okay. Yeah, I agree, because there are 3 rows over there, right? Okay. So let's talk about the trivial one, which will be the 0 of implication. If we can show that this guy here is false, empty range, do we have to bother showing this? No, because it is 0 of implication. Right? So strategy number 1. Show it is not the case R of I, because the 0 of implication goes like this. False implies anything P is equivalent to just true. Right? So we are using what we knew about some very practical theory, right? And this also nicely corresponds to what we talked about the array example before the break, right? Just you can also review it. So strategy number 1, if you can already show this empty range, you're done. Okay? What about strategy number 2? Let's say the range is not empty. Then this will be slightly harder, right? So now number 2, you want to show that R of I is actually true. And also you got to show that P of I is actually true. Both of them you have to show. Okay? Basically you want to prove the implication. Right? And this one, for example, you want to show that all the elements in a non-empty array are positive. So you can think about this case is trivial. Once you can shows that. This one slightly harder because you want to argue for every element in the range you can satisfy PI. Slightly harder. Are we good with this? That's how you prove it. Okay? How do we disprove it? If you want to disprove the implication, so now our goal is to show that it's false. So the goal over here is to show that R of I implies P of I is equivalent to false. And according to the truth table, there's only one way to show that implication is false, right? Which would be true implies false. You got the promised terms for the salary, but you don't really have the salary. So that means, sorry, let me say that again. You have the promised salary and you already paid that salary, but you didn't do the work. So the contract is breached, right? That's the analogy we did last time. So here, there's only one way. You want to show R of I and also not PI. That's what you want to show. Agree? Or another way, okay. Simpler way to put it. Give a witness. Such that, give a witness, let me use a different name over here, sorry. Give a witness J such that J is in the range, but it is not the case that P of J. Just give a witness, right? If I got an array that's non-empty, so how do you show that it's not all positive? Give me one element that's in the array that's negative. Okay, that's an analogy. So this is actually not that hard. You just want to find a witness. So this is not hard. You just have to give the witness to show that implication is actually false. All right? And for the existential quantification, it's not too bad because now we're dealing with conjunction. So the truth table is more straightforward. We don't have to worry about trivial cases. Okay? Let's say here. For proving the existential quantification is actually true, right? So our goal is to really show the conjunction is true, right? R of I and P of I is equivalent to true, right? So in this case, it will be easy. So I'll put a strategy here. Give a witness, let's say J here, such that R of J is actually the case. And also P of J is the case, right? You can show them separately, right? Let's say, is there at least one number in the array that's positive? Give me one element that's in the array and show that it's positive, right? Give a witness. And this one also is not hard. What's hard is the last case, which is to disprove the existential, right? Because if I want to say, okay, I claim that there is at least one element in the array that satisfies this. You're telling me, no, there's no way. You got to show me that every element in that particular array does not satisfy that. You're going to show in some way like a universal thing. So let's see this. Disprove, right? So the goal over here is to show this conjunction here is false. How many ways can we use to show that it's false? Well, there are two operands, right? Apparently there are two ways. Approach number one. Show that the range is empty. That's very easy. If you can show that the range is empty, there's no way for you to find a witness to prove it is the case. So it's false. So this will be the more like a trivial case for you. And this one will work because if you got false And P is just going to give you just false, right? If I can show that the range over here is simply false, doesn't matter what P is. What about strategy number 2? For strategy number 2, the last one, let's say Ri here is not really empty. There's really something there for us to consider. Okay? So you want to say Ri is the case, but not Pi. This will be the harder case for you to consider. This means you have to say, for all those I that satisfy the range, I want to show that all those I do not satisfy P. Right? I'll write it down for you. This will be the harder case. For those I satisfying I, it is the case that Pi is not satisfied. Do you really have to memorize the strategies? Not really. In some way, they're all derived from the fact that we got some specific pattern for all n exists. If you really forget about strategy, I would say, just remember we got these patterns over here. Implication for universal, and also conjunction for existential. And think about how can you show an implication to be false or true, and go from there, in case you forgot. All right. And let's now do some example, okay? And then we can move on to the last one, which would be some nice little rewriting to do. And then that's it for practical logic. Okay? How about we do some example here? How about we do 2? And then you can do the other 2 yourself. Why don't I choose, how about this one here and this one here? The other 2 you can do as exercise. You will see the solution on the slides. The second one will be exercise. And the fourth one will be exercise. Okay, the first one. Now, can you prove or disprove this universal quantification? First of all, is the range empty? Well, think about it. The range over here, we say x is an integer. X is in between 1 and 10. Apparently, it's not empty because we know that x really is from 1 to 10. Non-empty range. Or more formally, we know that it's actually, it's there. It's not false. R of x is not false. Right? Now, in order for us to prove or disprove it, in this case, you want to make a decision. Do you want to prove it or disprove it? If you want to prove it, you have to show that every x satisfying this is going to satisfy the property. Is it the case? Yeah, indeed. Because 1 is larger than 0, 2 is larger than 0, all the way to 10 is also larger than 0. So in this case, I can prove it easily. I just have to walk through all the elements in this range and show that it's larger than 0, satisfy it. Right? It's proven. Okay? But we're still applying the strategy. So here you can say all x in 1 to 10 satisfy this. All right? The other exercise I can tell you, that one is more about disproving, but give it a try. Right? I'll leave that exercise for you. And how about this one? Existential. Either prove it or disprove it. And the range over here, again, is not empty. The range over here, again, not non-empty range. If you want to prove it, you just choose one witness from this non-empty range. Can you choose a witness for that? Indeed. How about x2? Okay, I like it. witness will be 2, right? In that way, 2 larger than 1. The other one for exercise will be, you may have to argue that if the range is not empty, for example, you want to show that every element here is going to make this part false. That may be what you have to show, right, to disprove it. All right, any question about this? Yes? Sorry, say it again. So here, for the third one, right? Mm-hmm. Okay. No, it wouldn't be disproving it. So in order to disproving, okay, the question was, if you chose the wrong witness, let's say. Okay, it's a very interesting question. Okay, let me put it here. Guys, this is a very good question your classmate just asked. I'll put it here. By choosing a witness, let's say 1, which makes, if you think about it, 1 is an integer, and 1 less than or equal to 1 less than equal to 10, right? I'm just substituting x by 1 over here. And also 1 larger than 1, right? I'm just substituting here x just by 1 as well. You can see here, this part over here is true. This part over here is false. Evaluating 2, just false for conjunction. Now, is this witness enough for us to disprove the existential quantification? That's your question, right? Very nice question. Now, any feedback from all of you? Let me repeat the question again. By choosing this particular witness, we know that we can evaluate the conjunction over here to be false. Does that effectively disprove the existential quantification? It does not. Yeah, exactly. So in order to disprove the existential quantification, you have to argue for every element in the range that does not satisfy it. Right? Make sense to you? Okay. So guys, so here, no. So it is important for this conjunction here to be drawn here. Not sufficient. By just one witness. To disprove existential quantification. On the other hand, if you can use a witness to disprove the case for universal, yes, you'll be fine. It's different. Good. Yeah, I would say I really think that there's a very nice insight over here. So please make sure you understand the point I just made here. Please. Not sufficient. Okay? Think about it. All right, let's do one more rewriting about predicate logic, and then we're done for predicate logic. This might be it for today. We'll see. We've got about 6 minutes. Okay. Okay, so this will be the last little theorem you will see on the slides. I think just for completeness, let's see how we can prove it. It's actually a nice exercise just to kind of brush your mind about how to do proofs. You will need this kind of technique, not in exactly the same form, but later to do proofs. So what you will see on the slides is this. Well, we talked about proof strategy already. All is covered. Please review before next time. And then we got exercises, which I also discussed. You can see the solution as well. So now, how do we convert between quantification? That's the last topic for today, let's say. This will be the theorem, but it will be nice to see how we can justify them. In order to justify them from left to right, there will be some nice little axiom we can use. Let's do that. I'll do one. You can do the other. All right, and the same deal. I would like to leave the second one here as exercise for you. The second one here will be exercise. You can try. And let's now do this one here. I'm saying this one here, if and only if there's what equivalent to that. That's what I want to prove. And let me remind you about the axiom we have. We know that whenever you say for every x q of x, if and only if, over here, it would be not the case there exists x, not q of x. Do you remember that? Okay, let me, analogy, okay? Let's say this. I say for every student in 3342, they pass. How nice. What would be another way to say it? There does not exist a student that does not pass. Similar, right? Hopefully you like this analogy. Okay. Let's use this as an axiom for us, right? And now you can see q of x can just be this form. And not q of x, we just have to add some negation to it. Right? Let's now try to do this little proof. Okay? I got 4 minutes. That should be enough, and that'll be it for today. Let me start from the beginning. So I can say here, for every x, r of x implies p of x. Let's start with the left-hand side over here. I know that if and only if I can put some justification over here. According to what we have over here, let me write it down again. That's justification. We know for every x, q of x, if and only if not exists x, not q of x. You can think about the q over here is really this whole thing over here. Think about it. All right? Now, how can I rewrite it? I can rewrite it into, now I can turn for all into exist. Not exist x. And not here about qx, exactly here. R of x implies p of x. Right? You can see a nice pattern over here. You can see here double negation, right? And then this guy here is like a q over here. All right, almost there. And how do we go from here? Remember we talked about some rule or theorem for implication. When I say P implies Q, it's not P or Q, right? Why don't we do that? Okay, so now I'm going to say, I'll put it here. If and only if some justification, we know that P implies Q is equivalent to P, not P or Q. Not P or Q over here, right? Let's now do the replacement. So not there exists x, and not here, let's now do that. Not P or Q. So not Rx or Px, right? And then now we can do two things, just make it a little bit simpler. I want to do De Morgan. Not the case, or it can be what? I'll put it here. Not the case if I got P or Q is equivalent to not P and not Q. That's number one, De Morgan. Okay? And then double negation. If I got not P is equivalent to just P. Let's do these two at the same time. Okay? Finally, I can get not there exists x, double negation over here, so I'm going to get R of x. And over here, not Px. There we go. So this one here is corresponding to this one over here. All right? The proofs that you will be required to do in this course is not really in this form, so it can be a relief, right? You wouldn't be asked to do something like this, not quite. But I think it's a nice way to really brush out your mind about how you can support each step by certain rules. That's my main point over here. But I was encouraged to give it a try on the second one as well. Thank you so much. On Thursday, we're going to start with sets and relations, which will be even more fun, right?